This lecture is part of a series of lectures for Rad229 MRI Signals and Sequences offered in the Department of Radiology at Stanford University. The 11th lecture on radial and spiral sequences is divided into two parts. Lecture-11B covers spiral imaging. The learning objectives here are to explain the rationale for spiral imaging, to describe how a spiral waveform can be designed, to explain the trade-offs between number of interleaves, trajectory duration, and scan time, to explain how off-resonance and delays impact spiral images, and to explain the steps of a gridding reconstruction. So the spiral trajectory looks like this. It provides a flexible duration coverage trade-off. Like radial imaging, it starts in the center and moves out, so the echo time can be essentially zero. It has low first moments, making it insensitive to motion. We can use longer readouts to maximize the acquisition window. We can use variations of spiral, including Archimedean spiral, twirl, and whirl, and we can use variable density approaches, which can improve the signal-to-noise efficiency as well as the flexibility of the sequence. Here we start with an Archimedean spiral. The radius is proportional to the angle that we have rotated around the origin. If we express the k-space location as kx plus I times ky, we can use complex numbers and express k is equal to a times the angle theta, and theta is a function of time. Notice that this gives us a somewhat uniform density spiral, as shown below. We can use multiple interleaves to interleave spirals between the turns of the single spiral shown here. And in the extreme case, we can do a single shot acquisition with only one interleave. So notice, of course, that the angle theta increases by 2 pi per turn. So from this, we can calculate this constant A. So here is the formulation for the k-space trajectory. What we can see is that k is proportional to theta. We've added in e to the I theta, which is the angle of the trajectory. And then this constant A is essentially n over 2 pi times the field of view. What this gives us is as theta increases by 2 pi, we cancel out the 2 pi, and essentially this k-space radius is increasing by n over the field of view. In the extreme case, where n equals 1, the k-space radius increases by 1 over the field of view on each turn, which makes sense to support the field of view. As we go to more interleaves, we can space the trajectory further apart because the other interleaves will fill in the missing k-space. We can choose a stopping point that looks something like this, where the angle is set so that we reach some maximum k-space location here. And if we interleave, the interleaves will look something like this. And now the challenge is to design the theta as a function of time to meet the various constraints of gradients, sampling, and slew rate. So let's look at a sample design for an Archimedean spiral. We begin with the same equation. We can differentiate this equation to give us the first derivative and second derivative with respect to time. These will end up being written in terms of the gradient amplitude limit and the slew rate limit. From here, we can design the function theta of t to meet these constraints. And there are different ways to do this. So briefly, you can do approximations for theta of t, as explained here, and these consider what we will see later as the slew rate limited and amplitude limited regions of the spiral. We can also simply solve these numerically at each time point. We find the limits and we figure out which limit is going to be the active limit. And we can actually include the circuit model here, which is a little bit more accurate than the constant amplitude and slew rate limits. So this is an example of a spiral waveform here. You see the k-space trajectory kx, ky. You see the k-space over time, the gradients over time, the slew rates over time, the first moments over time, and the second moments over time. So again, this is an Archimedean spiral. The density is roughly uniform. The k-space amplitude is increasing over time. The gradient is initially limited by the slew rate because we're trying to turn very rapidly. Later, the gradients will be limited by the gradient amplitude or the field of view limit because we still have to sample along the trajectory. So on modern systems, we can sample very quickly, so we simply almost always will reach the gradient amplitude limit here. We notice that if we plot the first moment and second moment versus time, that these are very low at low k. And this is really important. This is where most of the k-space signal is, and this is why this spiral is often insensitive to motion. So now let's look at the spiral imaging sequence. We have a standard RF slice selective, and like radial out imaging, we have a very short TE because we're starting in the center of k-space. Here's the spiral trajectory that we're trying to follow, and the gradients are of course the derivatives of this k-space pattern, and they look sort of sinusoidal with increasing amplitude. And as we play the sequence, we can do different interleaves where we're simply rotating those gradients around, and the gradients look something like this. So now let's look at a question here regarding spiral imaging. So if we design spirals, we can use this function, which we'll explore in class, called VDS, for variable density spiral. So the question is, if we have 10 or 80 interleaves, which generates a shorter waveform with all other parameters constant? The second question is, which of these is slew rate limited for a longer period of the spiral? So this is the spiral for 10 interleaves, and this is the spiral for 80 interleaves. Not surprisingly, the spiral for 80 interleaves is a lot shorter. In fact, here it is about 2.5 milliseconds versus for 10 interleaves, where the spiral is closer to 20 milliseconds. The spiral for 10 interleaves makes many more turns because it has to cover much more k-space. Notice that the period of the slew rate is actually a similar fraction of the overall duration of the spiral waveform for both of these. So here, the 10 interleaf spiral is slew rate limited for a longer duration, and that's because the spiral is turning more tightly near the center. Let's now look at variable density spirals. Here the goal is to actually undersample the outer k-space to improve the imaging speed. One way to do this is to vary the spacing, which is 1 over the field of view, as a function of the k-space radius, or equivalently as a function of the angle theta of the spiral. Another thing you can do is increase the spacing along the trajectory. So here's our spiral equation, given again, but now the field of view is given as a function of theta. We can compare designs using variable density algorithms shown here. So the dashed red line is a uniform density spiral. The variable density spiral shown in blue is clearly much shorter. You can tell the trajectory is becoming less tight as it winds around, and this results in a shorter duration, although the comparison of duration is not shown here. The spiral is probably about 20% shorter. Spiral imaging is another example of a non-Cartesian sampling trajectory, and this requires some kind of a gridding reconstruction in order to efficiently reconstruct data. Because the data are irregularly sampled, we resample onto a grid to perform a DFT or fast Fourier transform. The grid mat function will be discussed in class, and this is a simple to read function that does gridding. So the goal of this is to resample onto the grid. If we look at the conceptual steps here, we will divide samples by the density at a given k-space location. We want to have a uniform signal if we grid all ones. So if all the samples are ones, we want the gridded signal to be uniform across k-space. We will then convolve the sampled k-space locations with a convolution kernel, which we call C of k. After the convolution, we resample at the grid locations, and we can do an FFT reconstruction. And finally, we can do what's called a deapodization in image space, which is a multiplication to undo the side effects of convolving with the convolution kernel. So here is a grid superimposed onto our spiral. Here are the grid points. And essentially, we take this convolution kernel, and in the neighborhood of each of the grid points, we basically take a weighted sum of the sample signals that were sampled on the spiral. We add these up, and this gives us our grid points, and after this we can do a discrete Fourier transform. So let's now look at the point spread function of spiral imaging. So unlike radial imaging, which had a streak-like pattern, undersampling in spiral will lead to swirl-like artifacts. As with radial imaging, there are rings of aliasing. We'll point out how the odd and even number of interleaves can change the character of the point spread function, which is actually common to spiral and radial out imaging. And we'll talk about variable density spiral. So here is an example of point spread functions for an even number and an odd number of interleaves. At the top, you see that the magnitude of the point spread function is pretty similar, especially in the inner ring here, which corresponds to inside the field of view. Notice that when you have an odd number of interleaves, you actually have a less coherent swirl pattern on the outside, which actually has lower energy. These are all plotted on a logarithmic scale. If you look at the bottom, if you take the real part, what's interesting is if you have an odd number of interleaves, and you can take the real part, you can actually suppress the first aliasing band. In practice, it is very difficult to do this very accurately because of other sources of phase. However, in practice, people often use an odd number of spiral interleaves. If we look now at the variable density spiral point spread function, we actually see that these rings become less coherent, which should not be a surprise because now there is no simple single field of view that is well defined in the trajectory. So with variable density spiral, we see less coherent aliasing artifact, and this should not be surprising because the trajectory is less uniform. Let's look now at the off-resonance sensitivity of spiral imaging, which is often one of the major disadvantages of spiral imaging, or challenges. So if we have a uniform density spiral, the phase increases roughly in proportion to k space radius squared. The spiral is often longer than the radial imaging for the reasons we've shown before, because we gain sampling efficiency with a longer trajectory. So this can lead to substantial broadening of the point spread function. You can correct for this off-resonance in the reconstruction. So at the bottom here, you show this phase, a map of the phase that accrues, and notice that we're going to a total of 4 pi radians in this example. And the point spread function on the right is substantially blurred compared with the reference point spread function below. So when we're designing spirals, we've talked about the number of interleaves, and we've talked about the algorithms, but there's a basic trade-off we have to make, which is similar to other imaging mechanisms. We want high spatial resolution, which demands a large extent of k-space. We want a minimal number of interleaves, which will help us reduce the scan time, and we want a minimal readout duration, which will reduce the sensitivity to off-resonance. So what we have to do when we design the trajectory is trade off between these features. So first we can choose a tolerable readout duration for off-resonance, and then we can trade scan time, which is related to the number of interleaves, for spatial resolution. So this is one approach. Here is an example. We've plotted spatial resolution as a function of temporal resolution, which can be considered the scan time or frame rate. So as we want to go to a lower temporal resolution, which means a faster scan, then we have to go to a lower spatial resolution, or more coarse spatial resolution. Notice that we could repeat this design by holding the scan time constant or holding the spatial resolution constant and trading off between the other two parameters. So we'll see an example of this shortly. It's worth mentioning that there are variations of spiral imaging that actually improve the speed of the trajectory. So these are called twirl and whirl, and whirl really builds on twirl. So twirl was first proposed and basically starts with a radial outward sampling pattern and then transitions into an Archimedean spiral. Whirl takes us a step further and actually does a non-Archimedean spiral that is instead constrained by the trajectory spacing. This leads to a faster spiral, particularly when you have a high number of interleaves, and there are MATLAB functions for this. So this is an example of comparing spiral versus whirl, and we've zoomed in on the outer trajectories here. So in Archimedean spiral, the spacing between these trajectories is 1 over the field of view, and this is in the KR direction, so this is radially outward. In whirl, what's looked at is the spacing perpendicular to the trajectory itself, and this looks like a very subtle difference, but it actually improves things substantially. Here we compare whirl to Archimedean spiral, whirl on the top and Archimedean spiral along the bottom. And the key point here is that whirl gives you a trajectory that is 10% shorter in time. So for a high number of interleaves, you can save some scan time. And if you look on the left, the trajectories look very, very similar. So clearly the trade-off is in the minimum duration. Now, you could argue that the Archimedean spiral is sampling for longer, so it has a little bit higher SNR. But it's interesting to think about the different design approaches that have been considered. So another variation that's quite interesting is to do a spiral in, spiral out. And this is sort of analogous to a full projection versus a radial out trajectory. This can be useful if you want to delay the echo time. Alternatively, perhaps if you're trying to sample at a spin echo, you can have a spiral in, spiral out, because the spin echo can be placed in the middle of the imaging trajectory. And to do this, you simply add a time-reversed gradient waveform. And this, if you think about it, will give you the spiral in, spiral out pattern as shown at right. There are also variations of spiral for 3D. The simplest, perhaps, is what's called the stack of spirals, which combines a spiral trajectory in plane with KZ phase encoding. There are variations such as cones or twisted projections, which sample the 3D space on the surface of a cone. And then there are considerably more other approaches that have been developed over the last 5 or 6 years that actually use more complicated patterns, but all of them are trying to efficiently sample 3D space. And most of them have similar properties to spiral imaging, where you can have a rather long trajectory. You have some sensitivity to off-resonance, so you typically have to do off-resonance correction for most of these trajectories. A topic that's actually quite important in fast imaging is how do we get back to the center of K-space? So this is the area of what we call preparatory gradients, which are similar to phase encode and phase rewind gradients. The difference is, in spiral imaging, we have to think about the fact that at the edge of K-space, our gradients may be non-zero, and our K-space is non-zero, and we want to be able to rotate the spiral waveform freely to do different interleaves. So what we want to do is basically create the fastest path back to the center that can follow an arbitrary direction, but how do we do this? So there are different approaches to doing rewinder design that we will probably see in our gradient design lecture later on. The goal is to bring both the gradient and the K-space back to zero very quickly. So one example for spiral is shown here, where the gradient just uses a simple trapezoid gradient waveform. The question, though, is how much power to use on each axis. Again, if we want these gradients to be freely rotatable, then we have to actually think about a two-dimensional problem for this rewind. So there are different solutions, including a finite segment method that was proposed, and convex optimization techniques, which we'll look at a little bit later in the course. Another comment that's important for spiral imaging is the impact of gradient delays. So the delays, as with radial, can lead to a mismapping of the center of K-space, and this can cause sort of a low frequency effect since it affects the inner K-space. In the outer K-space, delays typically cause a rotation of the image, so this is actually relatively easy to see as well as to debug. And then there are other effects again similar to radial imaging. So often in the case of these more complicated sampling trajectories, we'll actually want to measure the actual gradient waveforms to take into account delays as well as eddy current effects. So let's look now at an example where we've done gridding of a spiral acquisition. So we have a spiral trajectory here, we have 19 interleaves, we have a 20 centimeter field of view, and 1 millimeter resolution. So it's a 200 by 200 matrix. So if we're going to do gridding, we often normalize this to a scale that corresponds to inverse pixels. So notice that this goes from minus 0.5 to 0.5. But we've also scaled this back a little bit so that we can grid and then reconstruct onto a 256 by 256 matrix. So there'll be a small amount of interpolation in the image, which corresponds to the fact that the very outer K-space here is 0. So it's like 0 padding. So we grid the data onto a Cartesian grid that's 256 by 256. Here we can grid it onto a finer grid so that we can actually show the fact that we may have some spacing that may impact the field of view. Now we can inverse Fourier transform this, and I should mention that we gridded all ones here to look at the point spread function. So what this shows us is the point spread function amplified by 100-fold so that we can see the field of view from the 512 by 512 matrix. Notice in the 256 by 256 Fourier transform, we won't see this. So we need to actually grid to a finer grid in order to see that aliased sampling. Okay, and here we can scale the K-space down, and we can actually increase the grid size dramatically. What this will give us is a zoomed in look at the point spread function, and then we can plot the point spread function here. And you see that the width of the point spread function is on the order of a little more than around 2 pixels here. And that's because there's some interpolation going on here, but that's the shape of the point spread function from the spiral here. Okay. So this shows you how to use gridding with different grid sizes to look at the point spread function in more detail. Here is a design example for spiral design. As mentioned, we're often doing a trade-off. So let's say that we want the maximum number of cycles between water and fat at 3T to be about 2 pi, and we want 1 millimeter resolution over a 30 centimeter field of view. So the questions are, what is the maximum spiral duration, and what is the minimum number of interleaves to achieve this? So how do we get to this answer, which I should say is very hard to do in your head. So first of all, if we want that one cycle between fat and water at 3T, this means that the spiral duration has to be around 2.2 milliseconds. So what we can do is we can do some looping here, where we loop over the design, and if the duration is too small, we decrease the number of interleaves, and otherwise we increase the number of interleaves. And we basically do a bisection algorithm, and this can allow us to very quickly reach the desired length of the spiral and number of interleaves. So notice we started with 50 interleaves, and the duration is too long. It's around 4 milliseconds, and we're targeting 2.2 milliseconds. So we increase the number of interleaves, and now we find it's too short. And we basically split the interval, which is the number of interleaves. So next we go to 113, and we find that it's still too short, so we can split the interval again. And we actually fairly quickly converge to the final result, which in this case is 85 interleaves. So another question about spiral, which is easier to do in your head here, or at least on paper. If we look at a resolution of 1 millimeter over a 24 centimeter field of view, with 12 interleaves. The first question is, how many turns are there in each interleaf? And the second question is, how far does each interleaf travel? So the first part of the answer is to estimate the duration of each interleaf. And to do this, we can look at the 240 by 240 matrix. Remember, we have 12 interleaves, and each one is crossing the x-axis, say, twice on each turn. So this takes 10 turns. So if we take 10 times 12 times 2, we get to 240. So that gives us the number of turns in the interleaf. Now if we look at the k-space extent here, this is 5 inverse centimeters. So 10 turns at an average diameter of 5 inverse centimeters gives 50 pi inverse centimeters, or 5,000 pi inverse meters, or 15,000 inverse meters. So if we assume that we're at the full scale gradient strength of 40 millitesla per meter, this gives us a 1600 kilohertz per meter maximum here. If we multiply this by gamma, the duration here is 10 milliseconds. And if we actually go and design the trajectory here, we indeed see that we come very close to this 10 milliseconds. Okay? So we've basically looked at what is the length of the trajectory and the maximum gradient, and this gives us a very, very good estimate. And remember that this is because the spiral trajectory is very uniform. It's uniformly covering k-space, and it's more or less circular in a lot of cases here. So now that you've heard about different trajectories, including radial, spiral, and echoplanar, it's useful to do a very quick, rough trajectory comparison. So let's look at some of the features of these imaging trajectories that you've seen over these lectures here. So the first question is, do you need gridding? So for Cartesian imaging, you don't need gridding. But for radial, projection, and spiral, you always need to do some kind of a gridding reconstruction. And for EPI, you may need to do this if you're sampling on the ramps. We see that for spiral and EPI, we have some flexibility of the number of shots. So we can do single shot imaging or multi-shot imaging. And we have seen the pros and cons to doing both of these. Basically, it's a trade-off between the duration of each interleave or shot and the number of shots, which influences the scan time. We've seen that the center-out trajectories have a nice benefit of low first moments, and this is mostly with radial out imaging and spiral imaging. The effect of off-resonance is really important. In Cartesian imaging, we have a displacement. In radial out, we have a blur. In projection imaging, we may have a blur and some slight ringing and displacement. In spiral, we have a blur. And in EPI, we have a large displacement. If we look at the sensitivity to delays, in our Cartesian imaging, we rarely notice the difference. In radial out, we might get some signal loss. In projection, we might have some loss and artifacts. In spiral, we typically have a bit of a rotation, and in EPI, we have ghosts. So to summarize, spiral imaging gives us a flexible duration and coverage. We use a center-out trajectory, which gives us a short echo time and low first moments, which often give us desirable motion insensitivity. There are variations of spiral, including Archimedean, twirl, whirl, and variable density. The point spread function has circular aliasing rings with a swirl artifact outside. The off-resonance sensitivity can be a huge challenge and is often corrected in reconstruction, and of course this is a blur in spiral imaging. There are some variations, including spiral in, spiral out, 3D twisted projection imaging, 3D cones, and others. And we've talked a little bit about the rewinder design, which we will come back to in future lectures.